Today I'm going to talk about I2S interface and some basic simple design of digital audio amplifier design. So I think you know about the very well-known protocols in microcontrollers microcontroller using like I2C, UART and SPI. So this is the I2S different protocol in microcontrollers. So this is using for transmitting sounds, audio signals to the microcontrollers. So this means is integrated circuit sounds protocol. The main usages of this I2S protocol is we can use them in television audio system, car audio system, and telephone transmission cables. So then this is the block diagram for I2S data transmission. So you can see in here this is the transmission side. When we are putting analog signal from this, we are input analog signal through the microphone. Then there is ADC, like analog to digital converter. It converts that analog signal to digital signal. So then we can use this I2S interface to send this audio signal to our microcontroller. So then after we can process using digital signal processing or other kind of things to process this audio signal for CO. So this is the transmitter side of I2S communication. So after that, if we want to give some audio output from the microcontroller, we can also use this I2S interface for transmitting audio signals. So this we transmitting this audio signal as the digital signal, and there is in the speaker amplifier side there is a DAC converter, like digital to analog converter. It converts digital signal to analog signals. So after that we using class B amplifier for amplifying this signal for uh, amplification is magnitude of the signal. Then we can use speaker to get the output of the audio. Yes, so this is the receiver side of this block diagram. So we can this is the main block diagram for basic block diagram for I2S data transmissions. So yeah, in here, yes, in here you can see in the previous slide I talked about this digital signal transmitting. We use for digital transmission as the PCA modulation. So PCA modulation means pulse code modulation, and pulse code modulation is mainly mainly using techniques for in telecommunication industry. So what we are doing in here is we input our analog signal in the input section. Then we are going to sample that signal according to some sampling frequency. Like I can get my sample frequency like Fs. So I input this sinusoidal wave. Then I can sample this audio signal according to my sampling frequency. So then I send this you can send this sampled signal to the quantizer. So there are some two types of quantizers, like linear and non-linear quantizers. Based on energy wastage, we using some non-linear quantization levels, but the output is like this. Linear quantizing means we are approximating those signal values to some predefined values. Like if I use 3 bits for 3 bits for representing one signal. I'm using one symbol representing one symbol. I'm using 3 bits. So I have 8 quantization level in my system. So I can approximate the signal using according to one of each, one of them, one of quantization level. So after quantization part, I can like get output like this. In like this output from the system. So this is the quantized output, quantized signal of the my input analog signal. Yes, then we can get some encoding parts to convert this signal to 1 and zeros. Our main goal is converting this analog signal to 1 and zeros, like a digital signal. So for that we're using this PCA modulation thing. So as the encoding part, there are some encoding techniques like as Huffman coding and those kind of things. So there are using for there are some things so linear consider about the linear algebra and some things energy consumptions. So in encoding part, we are converting this thing this context signal to the digital data. Then if I use 3 bits for this, I have 8 quantization layers. So I can represent these quantization layers like 0, 0, 0, 0, 0, 1, 0, 1, 0. Also there I have 1, 1, 1 like 8 quantization levels. So I can use this encoding part for representing these quantization levels. So then I can send the signal as using these levels. Then I have the digital signal output. So this is the mainly main thing in happen in this inside this PCM modulation. So after that, uh, yes, after that, this is the main interface of the connection of I2S connection. So you can see this is the kind of similar to I2C interface. You can see this is the clock signals, and there is a data and there is a data signal, and only changes this is the word selection. Word selection means we can select the right and left channel for data transmissions. So as example, in the clock frequency, I can say I can use in the telephone signals we use 8 bits for representing one quantization level. On symbol I can use 8 bits. So then after that we can use as the frequency in the telephone signal we use as the sample frequency we use 8 kilohertz. So in the telephone lines also we have one data transmission line. So our then we can set the as the telephone signal clock frequency like 64 kilohertz. So this is an example for this kind of uh, I2S interface connection clock frequency. So then I go to this other I2S communication configuration when we can use in the microcontroller designs. So you can see these 3 configurations in the this transmitter and receiver in here. So we in this configuration transmitter is working as the master. So transmitter is controlling all the signal transmitting and receiving parts in as the master. Yes, in this configuration receiver is working as the master. So transmitter working as the slave. So in here receiver controls all the clock signals and word selection and word selection bits, and it can control the direction of the data transmission. So after that in this configuration there is a centralized controller in here. So it for this configuration controller working as the master. So it controls all the data transmissions and word selection and all the things as the centralized control. So after that I am talking about application of some simple application of I2S communication. I think you may don't know about this or don't know about this. In ESP32, it has two I2S interfaces. If we want to get in microphone input from the ESP32, we can choose this. You can see this is RX and TX side in the ESP32 internal controller. So if we want to get input from the microphone recording something, we can use this ADC for getting inputs, and if we would input this microphone signals from here, we can ADC converts that analog signals to digital, and RX to the RX side we can get into the CPU. We can directly access to the memory using DMA controller in the ESP32. Or if we need to transmit some audio signal from the ESP32, like we need to play some music from ESP32, we can use this TX side in the microcontroller. Then there is a digital to analog converter in here. then we can transmit this digital signal to analog signal as to the speakers. Yes, these are the simple thing in the internally happen in the ESP32. So for that, I need some inter I use for MAX 98357 module to implement that part in ESP32. These are the connection pins in ESP32. You can see we connect in the BCK pin into the GPIO 32, 33, and LRC pin for GPIO 25 and B pin for GPIO 32. This is the internal functionality of this MX module, and there are this the input we give input digital input to here this interface, and there is a digital dual converter, and there is a class D output amplifier for amplifying the signal. Also we can control the gain of the amplifier using this pin. There is a pin for gain, and also shutdown and channel select pin in here. So in class D amplifier means there is this the block diagram for class D amplifier. It's the like amplifying power amplifying circuit. We can use also there are classes like class A, class B, class AB, class C, class N, D, and class D amplifiers. So in I think you know about class A amplifiers. Mainly you are using in your A levels physics. You are learning about those BJT amplifier things. So this is the working as class A amplifier. In here they are using class D amplifier. In class D amplifier is in the this input is like analog signal, and they use some feedback uh, loop for uh, get some errors and input to this uh, system. Then it's convert those analog signal to the PWM signal. Yes, it converts to PWM signal. Then there is two MOSFETs in here, and it converts to amplified PWM signal. This input amplifier PWM signal. So after that, there is some filter using inductor and capacitor. So then it converts that amplified PWM to amplified analog signal. Then we can uh, get output from the our speaker as the analog output. Yes, these are the internal structure of the MX 98357 module, and this is the internal structure of how it's working in class D amplifier. So yes. Yes, this is the setup for ESP32, and I connected this MX 98357 module to ESP32 using this wires, and I connected my speaker to this connection, and I can connect my computer to ESP32, and uh, I can access to the ESP. There is a library for I2S communication, and also I can manually coding that one using there is a in the ESP32 reference manual. There are all the instructions here to do that coding part in the all the registers part and all the commands we need to know about the I2S interface. There are already in the documentation. So if you can need to coding yourself, you can try with this. There are all the things in datasheet. So then I'm going to do with some simple audio amplifier design. So in here I'm going to using is this I2S interface input, and then I convert it into the left and right audio signals. Yes, so for that I'm using this PCM1794 DAC converter. DAC means digital to analog converter. Then I'm using some this an amplifier for amplifying this audio analog audio signal, and then I'm connecting my speakers to here. This is the block diagram for audio amplifier I'm going to design. So this main thing is PCM 1794 DAC, and amplifier part and speaker part. So then, yeah, this is the sum of specifications of this DAC. So its output sync current is 3.9 milliampere and constant DC current is 6.2 milliampere. And this Texas instrument, these are produced by Texas Instruments, and we can use in DVD players, physical instruments, and audio systems. So yeah, output sync current means it has output currents. Okay, yes. In the DAC converters, we input digital signals. Then usually in the previous example, I'm using this DAC converter, this module. This DAC converter converts the analog signal to the voltage analog signal to voltage digital signal to voltage analog signals. So I can convert that to I can amplify with the voltage. So in this circuit, in this amplifier, in this DAC converter, that converts that analog DC voltage to analog current. So this output is like this. We input digital voltage, but it outputs two channels of currents. So it current means it has some variations about 6.2. It's like this 6.2 DC current, and it has a variation of 3.9 milliamperes. So this variance is 3.9 milliampere. It's in the data sheet already. So after before design part, we need to consider about the all the data sheet, all the things in data sheet about this DAC. So the other things I'm going to use is using is OPAs is 1612 op-amp and my headphone jacks headphones. So in the op-amp, it has I'm giving 5-volt power supply for this op-amp. So if I give 5-volt power supply, I can get maximum output as the plus or minus 4.4. So there is a 0.6 voltage drop inside the op-amp. So then if I use 5-volt and power supply, I can get plus or minus 4.4 volts for as the output. So in the headphone side, I'm using 10 millivolt power and 30 ohm internal resistance. So for that we should use 1.789 VRMS, so 2.529 V peak to peak voltage. I think if I use this kind of sinusoidal signal for this requirement, for satisfy this requirement, and with this I need to get 1.789 VRMS. VRMS means this some kind of DC output, DC volt measurement of the AC signal. So VRMS means V peak over root 2 in sinusoidal wave. Or we can use this V peak to peak value means this difference between two peaks. So if we can this is the voltage input for my headphone speakers. We need to give 1.789 voltage as the VRMS, so 2.529 voltage as the V peak to peak. Yes. So then in here I told you about this PLC deck is convert this voltage into the current. So if I need to this voltage, this deck is converted voltage into the current. So in here when we are doing this speaker side, we need to give input as the voltage. So when we in the amplifier side, we need to convert this current output current to voltage in the through the amplifier. So I'm in this kind of amplifier we can use current controlled voltage amplifiers, like controlled voltage amplifiers. So I'm going to use this kind of configuration. This my input is current my output is voltage. So there are also three other control amplifiers. So one of them is voltage controlled voltage amplifiers. So I think you know about that. Voltage control means my input is voltage, output is also voltage. So for that configuration, I can use BJT transistor. BJT transistor. So I can change the VBE voltage, and I can change according to that. I can change the VCE voltage according to that. Yes. Then as the second one, I can use voltage controlled current output. Voltage controlled current output amplifiers. Yes, it means I input the voltage and output. I can get output as the current. So for that, I can use MOSFET transistors. So as the MOSFET transistors, yeah, I can change this VG current gate voltage, and according to VG voltage, I can change the amplified drain current. So this MOSFET also we can use in the inside the multimeters. I think you know about this. Inside when we are working with multimeters, there is a configuration like we can measure resistance inside the multimeter. In the resistance, when we are using measuring some resistance, we need to change the our voltage. There is a no variable resistor in the inside the multimeter. So they are measuring that multimeter using this kind of MOSFET configuration. They are changing the VG gate voltage, and according to that, it's change MOSFET change the drain current. So then we can measure the drain current and gate voltage. Then we can find the resistance of the we measure in the circuit. So this is the way in the using it's another thing. So in this circuit design, I'm going to use in I'm going to convert this I current to voltage. So for that, I can use transimpedance circuit. Those are uh, identified as transimpedance. So yes, in this circuit, I'm using this kind of op amp configurations. Yes. So my input is here. You can see this the uh, current. They are using this current source for representing DAC output. This is DC current as 6.2 milliampere, and it gives some 3.9 milliampere swing current swing. Yes, in here, yes, then we need to know about, we need to find this R1 value and R1 value, R2 value and V bias value, voltage bias. So I need to add some voltage bias because I need to give this output voltage always in the positive side, always in the positive side. So I added some DC bias voltage in here. So this is the purpose of adding bias voltage for in positive side of positive inverting side of the op amp. So then I'm at VB for this, and I have some kind of V swing voltage in here. Because of this, there is a swing current in output from the uh, digital to analog converter. So there is also there is a voltage swing in the circuit. So I need to find this R1 value and bias voltage. So I can get, so find this R1 value. I need to get this voltage difference for this voltage difference. So in the, you already know the maximum output I can get from the op amp is 4.4. So because this is, I need to always maintain this op amp in the positive side. So I can maximum output we can get is 4.4 volt. So this in here, this voltage is EB. So you know about the op amp circuit, there is no difference between voltage. Is the low about that. So we can get this voltage as voltage difference is 4.4 minus PV. Then it's equals to like 4.4 minus is the kind of things. Then in when we are considering this diagram, this the maximum voltage we can reach is 4.4. So and also this voltage is swing between VB, swing around the VB, and we can after substituting from 4.4 to VB, we can get voltage swing. So it's equals to voltage swing, and it's equals to my voltage through the R1 into current through this resistor. So find this current through this resistor is 3.9 because this voltage swing is happen this because of this swing current. So there is a swing current from digital to analog converter side. So because of that swing, current swing, there is a voltage swing in that circuit. So I can find this voltage current. I can find this resistance using that current. So I'm using this equation 4.4 minus VB equals to R1 into 3.9. Yes. Also, I can use another this get as my first equation. So as the second equation, I am getting this VB. This VB equals to this is a DC voltage through the this resistors, like this in this DC voltage happens is because the DAC has DC voltage in DC current in 6.2 milliampere. So I can use this as PV equals to R1 into 6.2. Yes, yes. Then I can there I have two unknown variables like VB and R1. So then I can find R1 value and VB value. So after finding this one, then I can get R1 as the 432 and VB as the 2.68 volt, and I find this PS as I can get PS from substituting 4.4 from the VB from the 4.4, then I can get 1.65. Yes, 1.65. 1.85, sorry, 1.85. Yes. So then I find the resistance solution bias voltage. So then after I need to find this resistor value, this capacitor value. So I think you know about the capacitor resonance frequency. This capacitors are working as the low pass amplifiers, low pass filters. Low pass filter means it filter out the high frequency and allows the fast low frequencies. So in this amplifier, I am using this for I need to filter out the high frequency noise. So because of the human human frequency, hearing frequencies between 20 and 20 kilohertz. So I need to filter out higher frequency than 20 kilohertz. So I using this C1 capacitor for filter out those things, those frequencies. For finding out this one, you know about this equation F equals to 1 over 2 pi RC. To find RC equation. So after substituting this RC and F values, I can find these C values. So I can get C values as the 1.2 nanofarads. So I'm setting this getting 1.2 nanofarad as my capacitor. So it's the my transimpedance amplifier. So this capacitor and this resistor values using as the my transimpedance amplifier. So then after that I am going to transmit this voltage output to this differential amplifier. So in here, this is the differential amplifier configuration. I think you know about this because yeah, uh, in the differential amplifier configuration, this is the differential amplifier configuration. So we can amplify the voltage input difference to the as the output. We can get the output as the difference between the input voltage. So we difference between the input voltage is V2 minus V1. Then if we use R1 equals to R1, then R3 equals to R5, R4, we can get this kind of output. So V out equals to R3 over R1 into V2 minus V1. So this is the differential amplifier output. So according to that, I can design this kind of amplifier. So in the inside I using this previous op-amp for this, and I need to find this R3 value, R5 value, R6 and R4. For that, I'm assuming this R5 and R6 are equal to each other. And also R3 and R4 are also both are equals. So then I can change the equation to like this R3 over R5 equals to V out divided from V2 minus V1. V2 minus V1. So my V out is here. My differential amplifier is here. Amplifier output is here. So I am going to give this output to the speaker. So I need to get as the V out as the input in we previously calculated input voltage for headphones. I think it's 2.589 peak to peak voltage. Yes, it's the input of the headphones, but it's the output of from the differential amplifier. So we can get this input voltage of the speakers as the output of the differential amplifier. So and the V2 minus V1 is the swing voltage between the my output voltage from the my transimpedance amplifier. So swing between this voltage is I found that in found as 1.6 1.85 1.85. Yeah. Yes, then this is the difference between these peaks, and after that, after substituting these values, I can get like 2.589 divided from 2 into I, because I'm multiplying this 1.85 values because I'm using this whole difference, but I need this one, sorry, I'm using this swing value as the 1.85 as this one. So but I need this difference as the V2 minus V1 because V2 maximum V2 is here, maximum minimum V1 is here. So difference between V2 and V1 is this total voltage because this we need to multiply this 1.85 into 2. So after that calculating that I can get the ratio of R3 and R5 as the 0.75. So the thing is, now I know R3 over R5 ratio as it should be 0.75, nearly 0.75. So then I need to decide one value for R3, R5, R3 and R5. So for that, the thing is we need to consider in here, if I use the smaller value in R5 in this circuit and R3 for smaller values, this amplifier circuit thinks these are the load for this circuit. So if I use very low values for this amplifier resistors, this amplifier, this previous transimpedance amplifier things, these are the load resistors. So we can our calculation going to wrong for this. So if I use very high capacity, high values of high values for these resistors, this the power consumption of these resistors is very high. So then efficiencies will reduce for high power consumption. So I need to find the middle value for this resistance, and for that I will give a thing as the 500 ohms for R5 and 3 as the R3. I will get 375 ohms. So then I can get the satisfy this ratio and satisfy the previous trade-off, like this load resistance and power consumption things. Yes. Then after that I need to find this capacitor value. These capacitors are also used for cut off the high frequency values. As previous, we can calculate it from like previous equation. This capacitor values. Then I can add this my circuit for this resistors and capacitors for my circuits. So after that, this is the whole amplifier of the audio signal for audio signal. So I can input my digital signal from here. Yes, from here. So yes, from here, and there is a digital to analog converter here, and it gives some current output, and I can get using transimpedance amplifier to convert this current to voltage, and after driving through the differential amplifier, I can amplify those this voltage into the amplified voltage. Convert that, and then after I'm using this kind of speaker to get the audio output. So this is the total amplifier design of the using I2S interface. So this I can give input from the microcontroller to this circuits and get the output from the my speaker. So this is the thing I need to discuss on this session. So my session is I think it's over. Do you have any questions?